Hello, everybody. I am Lup from sunny Singapore. In this presentation, we talk about the NuttX drivers that we created to support touchscreen apps on PinePhone, like the drivers from MIPI Display Serial Interface, All-Winner Display Engine, Goodix I2C Touch Panel, and how we integrated them with the LVGL graphics library. If you'd like to download the presentation slides, please head over to this link lapyuan.github.io/NuttX. That's the letter L, not the digit 1. My presentation transcript, articles, and source code are available at that link. We were incredibly fortunate over the past year. NuttX now boots on a smartphone. That's the Pine64 PinePhone. NuttX on PinePhone works the way we expect. The LCD display renders graphics pretty well, and the touch input works okay too. NuttX won't make phone calls yet, but we're working on it. Also, thanks to the LVGL graphics library, we can create touchscreen apps for NuttX. In fact, we're using LVGL to build a feature phone app for NuttX so that PinePhone on NuttX will become a feature phone. Now there's plenty happening under the hood. MIPI, Display Serial Interface, Display Engine, Frame Buffers, I2C Touch Panel, LVGL support. How did we create all these NuttX drivers? How are they different from the microcontrollers with tiny screens? We shall find out today. PinePhone is a remarkable 4G smartphone, assembled with off-the-shelf components, designed for mobile Linux. Inside is the all-winner A64 SoC, system of a chip that runs 4 cores of ARM Cortex-A53, yet it's a 64-bit CPU. The components are surprisingly familiar: LCD display, touch panel, display controller, ST7703, LTE modem by QuickTel, Wi-Fi and Bluetooth by Realtek, MPU 6050 accelerometer. The components are sourced off the shelf, which makes PinePhone easier for learning and porting NuttX. To make sure we don't mess up people's phones, we boot NuttX on a micro SD card without touching the internal storage. No installation required. So PinePhone works like a normal phone, like an old iPhone 5S, which is also 64-bit ARM. All the components are there, just simpler, affordable ones. Our presentation today will cover the most complex component inside PinePhone, the LCD touchscreen that's connected on MIPI DSI, the Display Serial Interface. My background is in IoT microcontrollers. I'm familiar with SPI and ST7789 displays, but smartphone displays are overwhelmingly sophisticated. Inside the all-winner A64 chip is a display engine that renders pixels and pushes them to the LCD display over the display serial interface. Making this work with NuttX was a highly educational exercise. Thankfully, we didn't need to build all the drivers. NuttX provides some drivers, like the frame buffer interface, that makes graphics rendering a little easier. Most of this isn't well documented, so we created quick prototypes of the display drivers in the Zig programming language. Zig is safer, it has runtime checks, so we don't run into bad pointers inside our prototype driver. When everything has been tested okay, we converted the prototype drivers from Zig to C, which is not that hard since they are similar languages. Now this might look overwhelming, but yes, we need 11 steps to get the LCD display working on PinePhone. In a while, we will talk about the MIPI Display Serial Interface, or MIPI DSI, how we send MIPI DSI packets to initialize the LCD controller, and how we use MIPI DSI to render graphics on the LCD display. Sounds like we're pushing many pixels to render the huge display, but we don't actually create the packets to render this display. The all-winner A64 SoC does all this for us. Inside the SoC is the all-winner display engine. which reads the pixels from a RAM frame buffer and pushes the pixels over MIPI DSI to the LCD display. It sounds complicated, but we will explain this in a while. So why are we doing all this? Walking through the entire process of creating a display driver for PinePhone. Well, something fascinating has happened over the past year. Let us call it NuttX Next Gen. Traditionally, NuttX runs on 32-bit microcontrollers with tiny displays. But over the past year, NuttX has evolved to run on 64-bit smartphones and single-board computers, like PinePhone, PinePhone Pro, and Star64 JH710. These modern gadgets have enormous displays, connected on MIPI, display serial interface, and on HDMI. Yes, we are finally seeing the moment that NuttX goes high definition. I think it is awesome that people will be learning more about the inner workings of their smart gadgets by booting NuttX on their smartphones and single-board computers. But we have a major problem with NuttX Next Gen. Open source drivers are very rare for the consumer SoCs that we see in smartphones and single-board computers. We are slowly building up the NuttX support for these devices, bit by bit, driver by driver, in the absence of proper documentation. Yes, it feels a little tedious, a little painful. That is why we seek your contribution to fill in the missing NuttX drivers. Our presentation today will explain how exactly we created the NuttX drivers for PinePhone. Hopefully, we can follow the exact same steps to create the missing NuttX drivers for the next generation of NuttX devices. Today, we shall learn everything about the PinePhone touchscreen inside out, how we created the NuttX drivers for the LCD controller, display engine, frame buffer, and touch input, and how we built LVGL apps for PinePhone. We start at the bottom of the stack, the MIPI Display Serial Interface, or MIPI DSI. MIPI DSI was incredibly baffling to me. I'm used to microcontrollers and simple LCD controllers like ST7789. Why on earth would we need something so complex as MIPI DSI? Well, there's a very good reason for using MIPI DSI. If we think about our tiny embedded gadgets with ST7789 displays, we will remember that these tiny displays have RAM inside them. These are low-resolution devices, 320 by 240 pixels with 16-bit color. So having RAM inside is not a problem. But when we move to tablets and smartphones, we have a big problem. These displays are huge, 1280 by 800 pixels with 32-bit color. That is with alpha channel inside. Thus, we can no longer afford to have RAM inside these huge displays. Instead, we need to borrow RAM from our smartphone and tablet and blast the pixels continuously from RAM to the display over a high bandwidth connection with 4 data lanes. That's why SPI won't work for smartphones and tablets. We need MIPI DSI instead. So we begin with MIPI DSI, how we send commands to the LCD controller over MIPI DSI, how we render pixels to the LCD display over MIPI DSI. Underneath MIPI DSI is another layer, that's the MIPI Display Physical Layer, or MIPI D5. We won't talk much about MIPI D5 today, we just assume that it's already awake and talking. On simpler display controllers like ST7789, we mix the display commands and pixels into a single data stream. Thankfully with MIPI DSI, things are a lot better structured. These are the commands that we may send over MIPI DSI, like for initializing our LCD controller. To send an init command to an LCD controller, we send a DCS short write command or a DCS long write command, depending on the length of the command. DCS means display command set. Our commands need to be packaged as a MIPI DSI packet. There is a MIPI DSI driver in NuttX that will create MIPI DSI packets. But when we created the PinePhone driver last year, the NuttX driver wasn't available yet. So we shall explain how we created the MIPI DSI packet ourselves, and we won't need to do this ourselves anymore. But this exercise is good for appreciating the internals of a MIPI DSI packet. Inside a MIPI DSI packet, we have a packet header, the packet payload, and the packet footer. That contains a checksum, which is a 16-bit CRC, cyclic redundancy check. Inside the MIPI DSI packet header, we have the virtual channel ID, which is 0 unless we have multiple connected displays over MIPI DSI. Data type says what kind of command we are sending, DCS long write or short write. Also in the packet header is the word count, number of bytes in the packet payload, followed by an 8-bit error correction code. Our packet payload will have 0 to 65,000 bytes, and our packet footer will have a 16-bit CRC. Now all this is for a MIPI DSI long packet. For a DCS long write, there is a shorter variant, MIPI DSI short packet for DCS short writes. Short packets are more efficient because they don't have a packet payload and footer, but short packets will only hold 1 or 2 data bytes. Here are the steps to compute the 16-bit cyclic redundancy check and the 8-bit error correction code, ECC, for MIPI DSI packets. We copy and pasted the entire expressions into our MIPI DSI driver. So why do we need DCS short write and DCS long write for sending commands to the LCD controller? Well, it depends on the length of the command. For 1 byte, we send a DCS short write. For 2 bytes, we send a DCS short write with parameter, which is a longer form of DCS short write. For longer commands, we send a DCS long write. At startup, we will send a mix of short writes and long writes to the LCD controller. 20 such commands, in fact. We have seen the MIPI DSI packet structure. Now we write the code to compose the MIPI DSI packet. We could have done all this in C, but we chose to create our driver in an iterative, test-driven way. So we wrote it in the Zig programming language instead. This is how we compose the MIPI DSI packet in Zig. The packet header, packet payload, and the packet footer. With Zig, we can prototype and test our driver quickly, then convert our driver to C when everything is hunky-dory. Since our prototype driver is in Zig, we don't have to worry about buffer overflows, pointer errors, and other tricky bugs, all thanks to Zig's bounded memory sizes, instead of C's unbounded buffers. Hopefully, our Zig code is readable to programmers familiar with C, and actually Zig looks shorter, more concise than C. We talked about building our MIPI DSI driver iteratively. This is how we write the unit tests to verify that our driver produces the correct packets for DCS short writes and long writes. Here is a simple test case in Zig. It looks neater than the equivalent test case in C, and we don't need macros and other fancy coding tricks. So we have composed our MIPI DSI packet. How do we actually transmit the packet to the LCD controller? To transmit the packet, we write to the MIPI DSI registers in the all-winner 64 SoC, assuming that we have already enabled the MIPI D5, the MIPI display physical layer. To initialize our LCD controller, we need to send 20 commands, so we write 20 MIPI DSI packets to the MIPI DSI registers, and the LCD controller will turn on. Now that's only for initializing the LCD controller at startup. We will talk later about rendering the LCD display with the all-winner display engine. Remember that we created our MIPI DSI driver in Zig. After we have tested the MIPI DSI driver, we converted the driver from ZIG to C, which is actually not that hard. ZIG looks quite similar to C, as you can see here. It was a fun and productive experience creating a prototype driver in ZIG. I recommend it for folks who are creating new NuttX drivers. Finally, we're done with our MIPI DSI driver, and we're ready to send the 20 initialization commands to our LCD controller. We created our own MIPI DSI driver from scratch, but new projects should definitely make use of the new MIPI DSI driver in NuttX, like for PinePhone Pro and STAR64 JH7110. One final word about testing. Testing a new driver can be painfully tedious. For PinePhone, we need to flash in a micro SD card, insert into PinePhone, and boot the micro SD card again and again and again. How can we ensure that our driver is as bug-free as possible before actually testing on our gadget, so we can cut down on the cycles of flashing, booting, and testing? Based on my PinePhone testing, I have these suggestions. Write unit tests so that we can test each feature in isolation. In ZIG, we can do a compile time assertion check. So if we compute a register address incorrectly, the compiler will stop us at compile time. Test our driver locally on our computer before testing on the actual device. Test our driver locally in the QEMU emulator, just in case things look differently in ARM and RISC-V architectures. For our current work on STAR64 JH7110 single-board computer, we no longer boot NuttX on a micro SD card for testing. NuttX now boots over the network via TFTP, thanks to U-Boot bootloader. Our development of NuttX on STAR64 seems a lot quicker than PinePhone. We are all done with our MIPI DSI driver. Now we can send the initialization commands to our ST7703 LCD controller. Remember, this is only to initialize the LCD controller. Rendering pixels to the LCD controller will happen later when we talk about the display engine. This looks a little clearer in our roadmap. We are talking about step 7 here, initializing the LCD controller over MIPI DSI. The rendering will happen later with the display engine and the timing controller. Earlier, we talked about the DCS long writes and short writes, and how our MIPI DSI driver will compose and transmit the packets. To initialize the LCD controller, we need to send 20 of these command packets. Some of the commands are undocumented, but they were provided by the maker of the LCD display panel. So we just went ahead and sent 20 commands. Some of the init commands look similar to ST7789, in fact. Our LCD controller driver is implemented here. More details in this article. MIPI DSI operates in 2 modes, command mode and video mode. We have seen the command mode. We use command mode to send the init commands to the LCD controller. But to render pixels to the LCD controller, we will use video mode. This means our device will blast a continuous stream of pixels to the LCD controller over MIPI DSI. We do this because our LCD controller has no RAM inside to remember the pixels. This feels like the old days of CRT TVs, cathode ray tubes, blasting out the pixels raster line by raster line. Now, blasting every single pixel from our code will be highly inefficient. We'll probably get too busy to handle the screen refresh interrupts so often. Thankfully, the All-Winner SoC has an onboard hardware solution for blasting pixels. The All-Winner display engine and timing controller, T-Con. We will talk about them in a while. One last thing about the LCD controller, remember to power it up. On PinePhone, the LCD display panel is powered by the Power Management Integrated Circuit, or PMIC. That's the X-Powers AXP803 PMIC. It talks over an unusual bus, reduced serial bus. It works like a simpler version of I2C, and it's natively supported by the All-Winner SoC. We wrote our own NuttX driver for reduced serial bus. On newer boards like STAR64 JH7110, the PMIC dots over I square C. So the integration becomes a little easier. Now we come to the part that is probably the most sophisticated, the display engine inside the all-winner SoC. Each SoC maker will have their own variant of the display engine, so it will be an interesting challenge as we port NuttX to various SoCs. The display engine renders pixels to the LCD controller over MIPI DSI. It's all done in hardware. We don't need to compose any MIPI DSI packets. We simply configure the RAM frame buffers, and the display engine will do everything for us. No interrupts, no intervention needed. It works like this. The display engine reads the pixels from RAM frame buffers and performs some image processing, and pushes the pixels to the timing controller, Tcon. Together, the display engine and the timing controller will ensure that a continuous string of pixels will be pushed out to the LCD controller. This is necessary because there is no RAM inside our LCD controller, and we don't want to be too busy handling screen refresh interrupts. The display engine and timing controller will do everything for us. But first, we need to configure the display engine to render our frame buffer. So what exactly is a frame buffer? A frame buffer is simply a region of RAM in PinePhone that will be read by display engine over DMA, direct memory access. Pixels are laid out row by row by row. This is a typical frame buffer with 720 pixel columns and 1440 pixel rows, which is the resolution of the PinePhone LCD panel. Each pixel occupies 4 bytes in the ARGB 8888 format, 8 bits for the alpha channel, and for the red, green, and blue channels. Why would we need the alpha channel? That's because we'll be stacking up the frame buffers, as we will see in a while. The frame buffer looks plain and simple, but it works fine with the all-winner display engine. This is how we fill a frame buffer with color blocks. It looks straightforward, no surprises here. This integrates really well with text frame buffers, as we will see later. Can we render the Mandelbrot set in this frame buffer? Yep, sure, why not? Sometimes I wonder, why do we teach kids to program microcontrollers with tiny screens? Isn't it simpler to give them a PinePhone and blast the pixels directly from RAM? Now it gets complicated. Remember we said that the display engine will do some image processing? This happens inside a display pipeline. We configure the display pipeline to shift our pixels, or stretch the pixels, blend them, and so on. Each display pipeline is associated with a single frame buffer. We will come back to this. Just remember that a display pipeline is the same thing as a UI channel. We will use the terms interchangeably. Now, each display pipeline is associated with one frame buffer, and the all-winner display engine supports 3 display pipelines. Therefore, a total of 3 frame buffers can be mixed together and pushed out to the LCD display. The frame buffer at the bottom, we call it the base channel. The other 2 frame buffers, we call them the overlays. Here we have a base channel of blue, green, and red blocks. On top of the base channel, we have an overlay of a blue square. And on top of that, we have another overlay of a green circle. The all-winner display engine will happily render this stack of frame buffers into a single image and push out to the LCD display. This overlay will be super convenient for superimposing text, overlapping windows, and mouse pointers. The display engine supports video overlays, like for a set-top box with picture-in-picture, but our driver doesn't handle it yet. We configure the display pipelines to blend the 3 frame buffers into a single image. All this happens automatically over DMA. Once we configure and commit the display pipelines, the display engine will do all this in hardware. Here's how it looks in the official documentation for the all-winner display engine. Note that there is a video overlay plus a video scaler. Because of the multiple DMA channels, any updates to the RAM frame buffers will be instantly reflected in the display output, which makes it really easy to build our NuttX frame buffer driver. We will talk about the timing controller in a while. The all-winner display engine is surprisingly flexible when we configure the display pipelines. The display engine supports 3 frame buffers, and each frame buffer can have different sizes and offsets. So we could overlay a tiny mouse cursor on top of a full screen display. Always remember to commit the display pipelines after we configure them. This turns on the rendering and pushing of pixels to the display. Programming the frame buffers for overlays looks straightforward. Here we overlay a blue square, which is this, and a green circle, which is this, on top of the base frame buffer. Note that the alpha channel is in effect, which is why the blue square and the green circle are semi-transparent. We have seen how the display engine blends the 3 frame buffers into a single image, how it happens automatically over DMA. The blended image goes to the timing controller Tcon, which will push the pixels at a specific bit rate to our LCD controller. There is a second timing controller that pushes pixels to the HDMI controller. Thus, we can actually drive the MIPI DSI and HDMI displays simultaneously. But we haven't created the HDMI driver for PinePhone. Remember that the display engine reads our frame buffers from RAM and does this in hardware over DMA. This means that we have 2 things accessing our RAM at the same time, the ARM CPU and the display engine, which might cause problems. See the missing pixels in the photo? It looks like a mirage or a shimmering pond, but it's actually because our ARM CPU didn't flush the CPU cache after updating the frame buffer, and the display engine failed to pick up all the updated pixels. So folks, always remember to flush. We haven't implemented the flushing yet. We use a simple workaround instead. Just copy the frame buffer to itself, which works fine for now. As we have seen, the challenging rendering bits are implemented in hardware with the all-winner display engine. All we need to do is to update the frame buffers in RAM, and the display engine will read updated pixels over DMA and render them. This makes our NuttX frame buffer a lot simpler to implement compared to microcontroller displays like ST7789. Let us look inside the NuttX frame buffer driver for PinePhone. Why do we need a NuttX frame buffer driver? Later, we will be creating graphical apps on NuttX like LVGL apps. NuttX apps will talk to the frame buffer device to map the frame buffer into memory and render the pixels into the mapped frame buffer. That's why we create a NuttX frame buffer driver for NuttX apps to render pixels to a display. We talked about this earlier. A frame buffer on PinePhone is simply a flat array of pixels, 32 bits per pixel in ARGB 8888 format. This is how we represent the frame buffer inside our NuttX driver. Inside our NuttX frame buffer driver, we describe the base UI channel with a plain info struct. The base UI channel is a frame buffer at the bottom, underneath the overlay frame buffers. We point the struct to the frame buffer from the previous slide, and we set the dimensions of the frame buffer. 720 pixel columns by 1440 pixel rows, which is the resolution of the LCD panel in PinePhone. How do we tell NuttX that we have 2 overlay buffers? We describe this with a video info struct inside our NuttX frame buffer driver. This struct tells NuttX that we have 1 base frame buffer plus 2 overlay frame buffers. Then we define the standard frame buffer operations for our frame buffer driver, getting the video info, plain info, and so on. Remember the pixels that got dropped because we forgot to flush? The update area operation is the right place to flush the CPU cache. right after we've updated the pixels in our frame buffer. And that's all for our NuttX frame buffer driver. The all-winner display engine will do most of the rendering work for us. That's why there isn't much code inside our NuttX frame buffer driver. We have completed the rendering of graphics to the LCD display, but NuttX on a smartphone will be terribly boring unless it supports touch input. Let us talk about the Goodix I2C touch panel inside PinePhone and how we created the NuttX driver. The LCD panel in PinePhone is bundled with a Goodix 3T917S capacitive touch panel. That's the CTP in the schematic here. Goodix touch panels are quite common in the world of microcontrollers. The touch panel in PinePhone works the same way, just upsized to a bigger form factor. When we touch the touch panel, it triggers an interrupt over GPIO. Then we read the touch coordinates over I2C. Some Goodix touch panels have a complicated power saving mode. They won't respond to I2C requests unless we tap them and wake them up. Fortunately, the Goodix touch panel in PinePhone is a lot simpler. The power is always on. Goodix touch panels tend to be poorly documented, so we wrote our own docs. Now, since the touch panel is undocumented, how do we figure out how it works? We started by writing a loop that polls the touch panel, wait for the GPIO to transition from low to high, then we read the touch data over I2C. The raw data from the touch panel looks like this. After we figure out how to pass the touch data, we convert this code into a proper NuttX driver. Polling won't work in a NuttX driver, so we change our code to work with GPIO interrupts. We must be careful with interrupts. If we don't configure the GPIO interrupt correctly, we might get a flood of interrupts. Each dot here represents a GPIO interrupt triggered by the touch panel. This is very bad because NuttX gets too busy servicing the interrupts and NuttX can't even boot properly. Finally, we come to the top of the stack, LVGL applications that will call everything that we have presented today. This will allow us to create and run touchscreen applications on NuttX for PinePhone. Fortunately, LVGL works out of the box on PinePhone. We didn't do much integration that's specific to PinePhone. That's because LVGL on NuttX is already integrated with the NuttX frame buffer and the NuttX touch driver, which are already supported by NuttX on PinePhone. Note that the LVGL library polls the NuttX touch driver periodically for touch input. It's not super efficient, but it works okay for now. We switched the default LVGL font to a larger font. Somehow the LVGL demo apps were designed for tiny screens. This is probably the first time that LVGL apps will run on a big screen. LVGL performs quite well on PinePhone. The LVGL benchmark says that PinePhone runs at 20 frames per second, which is reasonable since most of the rendering work is handled in hardware by the all-winner display engine. We are experimenting with LVGL in fun new ways, like creating LVGL apps in Zig and running them in a web browser with WebAssembly. We have a presentation on that. Check out the link below. Since we have LVGL running on a smartphone, can we create a sophisticated LVGL app that is actually useful for a smartphone? That's why we created the LVGL Terminal app. The app lets us run NSH shell commands on PinePhone by typing on the on-screen keyboard. It works by spawning a POSIX task and talking over POSIX pipes. Here is PinePhone running the standard LVGL benchmark app. The LVGL benchmark says that the PinePhone rendering performance is 20 weighted frames per second, which is quite good for the big display that we see on PinePhone, all thanks to the all-winner display engine inside PinePhone. Here are two demo apps that were bundled with the LVGL library. At the left, we have a forms-based dashboard app with all kinds of LVGL widgets. At the right, we have a simulated music player, which doesn't actually play any music. Again, they work very well on PinePhone, even though LVGL library was created for tiny screens. Next comes the LVGL terminal app that we created specially for NuttX. It works like a serial terminal app, except that it is graphical and touch enabled. Here we're running some NSH shell commands and viewing the output from the NSH shell. What's inside our LVGL terminal app? How does it work? Remember that the app lets us run NSH shell commands by typing on the on-screen keyboard. The terminal app begins by spawning a POSIX task for the NSH shell. When we type a command, the app sends our command to the NSH task over a POSIX pipe. The NSH task executes our command. The output from the NSH task goes into another POSIX pipe, which channels the output to our app for display. It's a simple LVGL app that works really well with POSIX tasks and POSIX pipes provided by NuttX. I hope our presentation today will be helpful to folks who are creating NuttX drivers for the next generation of NuttX devices like PinePhone Pro, Star64 GH710, and IMX8. We are now building NuttX drivers for 64-bit SoCs that are found in many popular consumer gadgets. Maybe someday NuttX will run on all these gadgets. Smartphones, single-board computers, tablets, laptops, even handheld gaming consoles, across all flavors of Pi. These SoCs have their own implementation of MIPI DSI and display engine, but just follow the exact same steps that we have meticulously documented today. And we will probably produce a NuttX display driver that works okay for these SoCs. Right now, I'm working on a NuttX display driver for Star64 GH710 single board computer. We see the exact same features as PinePhone's display engine: DMA, layers, overlays, display pipelines, MIPI DSI, and HDMI displays. This shows that modern 64-bit SoCs all render displays the same way. Hopefully, we will have a NuttX display driver for Star64 GH710 real soon. Coming back to PinePhone, everything that we have covered today is documented in these articles: display serial interface, display engine, LCD panel, frame buffer, touch panel, LVGL, WebAssembly, and our feature phone app. NuttX on PinePhone has been an incredibly rewarding journey, thanks to the awesome NuttX and Pine64 communities. As NuttX evolves to support the next generation of gadgets, I hope we will have many more NuttX drivers for all kinds of LCD displays, HDMI displays, and touch panels. Thank you.